putting all of the machine learning algorithms, models, and everything else into the database didn't always sound like a good idea to me. A lot of this is based on things that I learned working at Instacart over the last decade, trying to scale our machine learning infrastructure, our data infrastructure, and our real-time inference systems. When I got to Instacart, one of the first things I did actually was help pull all of our product catalog data out of our monolithic Postgres database that was already hitting scalability constraints, 8, 9 years ago. And I moved all of that into Elasticsearch so that we would have this beautiful, horizontally scalable, amazing natural language processing framework. And that actually carried the company for about the next 5 years. It became the real heart of our data infrastructure. And it allowed us to grow the business to a multi-billion-dollar revenue generating enterprise. Our Elasticsearch cluster grew to several hundred nodes. It was powering several thousand stores worth of data with hundreds of thousands of personal shoppers and millions of customers using it on a regular basis. We were doing everything with that cluster. We were taking our machine learning embeddings and putting it in there. We were putting our feature store data in there. Some of the JSON blobs for our Elastic documents reached the size of megabytes. And over time, this became slightly less tenable. Once you have the God object in your data architecture that everybody wants to put something in and get something out of, there's all kinds of organizational problems. There's also all kinds of scalability problems, regardless of the technology, and you really need tight control over everything going on. The crucible moment, I think, for me came during the COVID pandemic when most of the world moved from an offline grocery experience to an online grocery experience. We were already a multi-billion-dollar company, and then we started doubling on a weekly basis. And at that point, everything you know about scalability goes out the window. Everything you know about engineering best practices goes out the window because the company's going to die if you can't actually scale double in a week. And then you have to do it again the next week. And so you find all of these microservices that had their individual feature stores based on Redis or Cassandra or Druid, or we're talking directly to Snowflake. All of the concurrency issues that you thought you would slowly deal with all come to a head. And so what we did was we had a Postgres cluster. We had learned a lot about scaling Postgres in the intervening years between the time that I get there. You can get pretty far with read replicas, especially in a machine learning context, where a few seconds of data latency is actually pretty state-of-the-art. When you start thinking about Kafka and Flink streaming, then you're used to tolerating and not having ACID-compliant transactions. And so we can actually scale Postgres in a very similar manner horizontally. We get really good control of the sharding capabilities of our database so that we can very specifically target exactly what criteria we need. And we abstracted all of that logic that we built internally in Instacart into a different project that I'm not going to talk about today called PGCat that sits in front of a massive cluster of Postgres databases to help scale it horizontally. But just know that that's always the other half of the project that I rarely talk about because scaling Postgres is so important when you're talking about machine learning. Talking about machine learning, when we think about machine learning, a lot of people in the world think that it's this mystical, dark art. And I think that's really unfortunate. I think that we should try to take a engineering first approach because I think engineering is actually where many of the hard problems in deploying machine learning systems are. And I think engineers are very used to dealing with systems as black boxes. You have inputs, you expect outputs. It's just a function in the middle. A machine learning model is just a function. It just takes inputs, it just produces outputs. You don't need to know how it works to use it. We use hundreds of APIs, hundreds of functions, hundreds of SDKs without really knowing how they work internally, and we do this very effectively. We have unit tests, we have integration tests, we have end-to-end QA, and we can deal with machine learning systems very similarly and get very far. So this is an example. It's very contrived. It's just a function that takes your age in years and it returns a float. Or I'm sorry, it takes a birth date and it returns a float. This is implemented in Python. I hope that I don't have any bugs in my code, but it gives you a rough idea of what we're talking about. We can actually pretend that we're a machine. We don't understand birthdays. We don't understand age as a concept. And so if we're trying to teach a machine about how to calculate a birthday, we'll take a data-driven approach. We'll collect some samples from the audience. You know, somebody's born in 1960, somebody's born in 1980, somebody's born in the year 2000. And we can ask them, what is your age? We don't know how they're calculating their age. It's some internal mystical black box that they know how old they are and they know when they were born. They'll actually do some computation very similar to that Python function, but we don't need to know that. So we can just put their data in a lookup table, and now our function implementation doesn't need to know anything about dates or ages. You pass in a birth date, we'll look up that birth date in our data table, and we'll return the answer. This is actually pretty terrible because most people in this room wouldn't have an exact birth date, and so we'll get a not found error rather than actually returning a useful age. So this is where machine learning comes into play. What we can do with this very meager sample of data is we want to generalize, right? We want to be able to tell people their age in years given any birth date, not just some birth date that somebody's already told us the answer for. One of the simplest machine learning algorithms is linear regression. And all linear regression is you take your 3 data points that you have, you put them on a plot graph, you draw a line through them. And if you remember, you know, the slope-intercept form of a line from early algebra in high school is y equals mx plus b. In this case, we know that, you know, every year you get 1 year older, and it happens to be the year 2023 today. So m is -1, b is 2023. This gives us, we've now solved the equation for the linear regression that passes through these points. You don't need to know how linear regression actually works, actually implemented. That's just another function call. It'll give you this data. There's libraries that do this. It's all implemented. We can now rewrite our Python function. We have a couple constants. We have m and b. You can now pass in your date time. The year of the date time is the only feature we care about in our very simple model. We can now multiply that by m and add b. And now we've actually generalized our 3 data points into predicting the correct age from any birth date without really knowing anything about ages or birth dates. And so if you start to think about all the hidden functions in our applications from our user perspective, we don't know why users behave the way that they do or what they want, but we can start to gather data about their behavior, and they can start explaining to us these hidden functions, and we can model them. And then we can actually generalize those models across populations. So machine learning is a very, very powerful technique when you're dealing in a murky environment. To move this forward, you know, beyond the simplest linear regression, neural networks, deep learning, and LLMs are a much more advanced topic. This is a diagram of a very simple neural network. It has 3 layers. The 3 layers are the inputs, the hidden layer, and the output. This is just a function. It takes 3 inputs. It produces 1 output. What happens in the middle is a black box. Nobody needs to know. But I'll walk through an example. And just for reference, all machine learning models only operate on math. They only take numbers. But what we've seen lately is that LLMs, they take text. And so how does that work? Well, you start with your words and you assign all of your words an ID. So A is the first word in our dictionary. It gets the ID number 1. A pawn is the 74th word in our dictionary, so it gets the ID number 74, and so on and so forth, until you have all of the words in your dictionary assigned numbers. Then you multiply those numbers, you add those numbers. Every single line in this graph represents a function very similar to linear regression. There's hundreds of different functions and hundreds of different ways that you can implement those lines, but you don't need to know that right now. You don't need to be a machine learning expert to know that this is just math. It's a lot of math. There are a lot of lines, and you know, that's why GPUs can actually execute all of those lines in parallel. They're all independent, But what you'll get is just some more magic numbers in an array. In the middle, in the hidden layer, you just repeat that process with more lines, more functions, more math, and you'll get an output. And the output is just some number, some magic number like 42. So to actually understand what 42 means, and we look it up in the dictionary and we get the word timeout. And so now we have this model that, given the 3 inputs, once upon a time, is predicting the next word in the sentence is time. Oh. And this is how LLMs work. This is the magic that they do. But for this talk, we're going to focus on embeddings and vectors. What are embeddings and vectors? An embedding is just that hidden layer. This is some mystical intermediate representation that the model has. State-of-the-art research doesn't really understand why these numbers are the way that they are. They are the way that they are because that's what gets the right answer. It's basically what it boils down to. There are lots of clever ways to figure out how to generate those numbers to make sure that you are getting the right answer. But again, we don't need to know any of that. It's just a black box. It's just a function. The very cool thing is that we'll have lots of various ways to start a story, like once upon a, that may all be similar to us, and they will also be similar in this hidden layer, in this embedding, even though they may use completely different words. It may be a completely different phrase. It may be a completely different language. As long as the model has been trained well, then the embedding, the intermediate representation of that language will be very similar. And so, and when I say similar, I just mean like by Euclidean geometry. Like the number 3 or -3 will be close. It'll be some number close to -3. It'll be some number close to 23 in the second box. And we have lots of ways to measure similarity of large arrays. You can do the Manhattan distance since we're in New York. Or you might choose the dot product, or you might choose cosine similarity. These are all just for loops to implement these things. Again, modern processors can do a lot of those computations very, very quickly and tell you how similar all of these things are. The reason you need a embedding database, or you might want an embedding database, is think about the Elasticsearch case that I mentioned before. You have hundreds of thousands or millions or even billions of documents, and they're all text. In traditional search, you're going to do keyword matching against an inverted index using English language. But if somebody uses the wrong word, if they say, I'm trying to come up with an example, vanilla ice cream versus old-fashioned vanilla, you may not actually get the right keyword match, and you may return the wrong product. So synonym matching is something that embeddings are very, very good at. And so you can actually take all of your natural language documents, you run them all through a neural network like this, you generate the embedding for that document, and then you save just that embedding, just that array in your database. Now, pretty much every database I know of has an array data type for storage. It's a pretty primitive data type. Pretty much every programming language supports arrays. Even garbage collected runtime languages like Python can implement operations on arrays very quickly, especially with optimized libraries like NumPy and Pandas. So this is not new stuff. Even though vector databases seem very new today, people have been doing these things for decades. And a lot of the functionality you need has actually been baked into hardware by Intel and by NVIDIA, because this is such a generally useful thing to be able to, say, add up the numbers into arrays. Like, everybody needs to do it for all kinds of things. But if you have a database and it's full of these arrays with millions of them, and then you have a user query come in, you can also generate the embedding of that user query. And now you can actually calculate the distance between that user embedding array and each and every one of the arrays in your database. And you'll get some distance function for all of those. You can sort that list, find the one with the smallest distance. That will give you the array. You translate that array as mapped back to a text document. And now you have the English language document that is most similar to the English language query coming in. And again, this is just a function. You take a single input, which is English language, you produce a single output, which is English language, even though it's all math under the hood. So I've just given you a pretty low-level or high-level description of how machine learning works. You can basically forget all of that now, because if you want to generate an embedding, you don't really need to know how any of it actually happens. We've created a very simple function in PostgresML. If you install PostgresML in your Postgres database, you can select the PGML embed function, and you pass it 2 arguments. The first argument is the model name, and this can be any model published on Hugging Face. There are hundreds of open source models that will generate embeddings. This can be a model that you've trained yourself if you are a natural language processing expert. And then it, of course, takes the text that you want to create an embedding for. And so you can use this function both to index all of your documents and create embeddings. And this is the output of that function for a single call. It's always a vector. And again, a vector is just a massive blob of numbers. Keep in mind, though, that when you're talking about these embedding vectors, typically they're on the scale of 1,000 floats each. And so if you're talking about 1 million documents that you're creating embeddings for, that's 1 million times 1,000, 1 billion floats that you need to store. That's a gigabyte. Yeah. So these things can quickly grow large. And so you do need to be thoughtful about how you're storing them, how you're indexing them, et cetera, et cetera. But Postgres makes this, again, very simple. If you have a documents table, and that table would normally have a text column that represents the body of the document, we can add a separate column or a second column to that table. And this table will represent or hold the embedding. In this case, the embedding is a vector. It has 768 elements in it. These need to be sized. It's really nice to have a typed schema in Postgres where you can check correctness of everything. But this particular vector column, Postgres has this really nice feature where you can say that a column is generated. And in this case, the generation of this embedding column is our PGML embed function. So anybody who inserts some text into this document table is automatically going to also create an embedding alongside that document. They don't even need to know that they're creating an embedding. It eliminates a lot of issues with data staleness. If they update the document, the embedding is also regenerated and updated for them. This is an example of a slightly newer model. It's the Hong Kong University's Natural Language Processing Instructor Extra Large model. At the time that I made these slides, it was the leading model. It's no longer the leading model for embeddings. These things change on a weekly basis. So being able to just swap out your model name, regenerate all your embeddings is actually really nice. But this model is interesting because it takes a prompt for how to actually generate the embedding, similar to all of the prompt engineering that people are doing with other large language models. So it's worth calling out that everything is moving very, very quickly now. You need a lot of flexibility, and you need to constantly be updating dependencies. Python dependencies are not fun to maintain. There's a very large operational burden there. If you're doing machine learning on a bunch of laptops for your data scientists, it's very hard to make sure that every data scientist in a large organization has the latest updates and that their laptops are working. On the other hand, if there's one large central database cluster, that thing can be managed very effectively by an operational team who has complete control. And then the data scientists can still get access to the latest models. They can still get access to do all of the things that they need to do. PostgresML isn't just about large language models. It has all of the classical machine learning algorithms that you expect. We have native bindings for XGBoost that are super, super fast. We're very proud of. The implementation is highly optimized so that when you have what is an array, a C array in memory in Postgres, in a buffer from a table, We take a pointer to that. We don't even copy it. We pass that pointer to XGBoost. XGBoost says, fine, I know what an array is. Again, these things are very primitive. This is the goal of Apache Arrow. This is the goal of Protobuf from Google. They have Spanner. Spanner is a very similar concept that when you have a protobuf, will store the data in the array, or the data in the table in the row in the exact protobuf format. So there is no serialization. They can just copy it straight out over the wire. Serialization and going over the wire kill so many machine learning applications. They really limit the amount of data that you can bring to bear in an interactive online context. But that's an aside for later.
Stored keyword in 768. Can you explain those? The stored keyword in 768.
Yeah, so the Hong Kong University Natural Language Processing Instructor XL model, it has a hidden layer in the middle of it that is 768 nodes wide. And it will always have 768 floats as its intermediate hidden layer representation. And so regardless of the string size that you pass in, it's gonna have that hidden state once it's read the entire string. And so that is the size of the vector that we will always be storing in this table, regardless if it's 1-word input or 1,000-word inputs. A lot of these models have what's called a context window, which means they can only consider 512 or 2,000 tokens at a time. If you pass fewer than that, it will get padded out with zeros or the empty word token. If you pass more than that, it'll probably just get truncated. There's a whole bunch of techniques that you might want to do called chunking, where if your documents are larger than the context window of your model, you will want to split those documents up into chunks, create an embedding for each chunk. There's lots of cool tricks you can do with embeddings. I don't know if I'm covering this later in the talk, but you can do all kinds of math with arrays. You can add, like, let's say you have a document and you break it up into 10 chunks, and you generate 10 different embeddings for those 10 chunks. You can actually add up all the vectors, and the vector that you get by adding up those 10 vectors will actually be the average vector of the entire document. And so you can, even though your model may be limited to a context window of 512, the embedding practically that it can consider is unlimited. But if you think about what happens when you start adding up a bunch of embeddings together, some will have positive numbers, some of them will have negative numbers, a lot of them will just cancel out and trend towards 0. And if you add up, the embeddings for all of Wikipedia, you might just get zeros across the board, meaning that this is not special in any way. It's equally relevant to everything or equally close to everything. Well, it'll actually be closer to things that are also very generic or general. And so that covers, I think, the 768. Generated always as is just the Postgres syntax that tells Postgres anytime someone inserts or updates a row in this table, it needs to run this function. And I'll step over here. This body here is actually a variable that references this body column up here. So you only have to pass the body text in once. Postgres has it in memory once. It will reuse it and it will repass it to the model here. And stored is another option. You can have this be stored in the table physically where it will take up space. And this is good if you read things more than you write them, but you don't have to store it. It can be generated on the fly at read time. So perhaps you're storing a lot of documents that you never need the embedding for. Generating embeddings is expensive. So in that case, you only want to run the generation function if somebody's reading the embedding column, and that might be a savings there. This is an example of the cosine distance operator that's also provided by PG Vector. There are 3 of these operators passed. This will do the cosine similarity function. There's one for the Manhattan distance. There's one for the dot product. These 3 functions have different trade-offs. Manhattan doesn't involve any square roots. You just add up the east-west plus the north-south, and that's your final distance. Whereas dot product and cosine similarity have a little bit more math involved. They're a little bit more expensive to compute, but the distance is truer. You know, if we actually take the hypotenuse of the triangle, that's better than if we look at just the east-west, north-south Manhattan distance, although we've just had to calculate a square root. So, you know, my preference is to always start with cosine distance, which is the most flexible. If your vectors are normalized, then you get the dot product will give you the same accuracy for free, but not all vector spaces are fully normalized. So this is the safest, highest quality answer. If you need more performance later, you can test empirically, and you really have to test empirically. There's all kinds of metrics you can get for these models that will give you a quantitative answer of like, oh, the perplexity is blah, blah, blah. And like, what does that mean? I don't know. It means it's better than the other one, maybe, kind of. What you really have to do is you have to actually run some queries against your database. You have to look at the things that you're getting back. And you can actually, you know, later on we'll get into some other ways to look at quality. So I'll leave that for then. If you have, say, 1,000 vectors, you can, a modern CPU core or GPU core can, with several gigahertz of speed, can probably compute 100,000 cosine similarities or dot products per second. And so if you have 100,000 documents in your database and you have a single core CPU and 1 second is fast enough for your application, then you're done. You don't need anything special. If you have fewer documents, you're done. You don't need anything special. A lot of document collections that I see are on the order of like thousands. They're not on the order of millions. And you can just brute force the computation on a single core. Now, if you have a GPU that has 5,000 cores, then you can do 5,000 times 100,000 in a second, which will give you 5 billion documents. 5 billion is an interesting number for scalability reasons, but that's probably a different conversation. In this case, though, like let's say you have 1 million documents, and you don't want to wait 10 seconds for a user query to come in. You need a way to actually find your closest vectors in your data set much more quickly. And so you want to avoid doing a lot of the direct comparisons. And so you use indexes to create shortcuts all of the time. Most people are probably familiar with keyword indexes when they're doing text recall. We just build the list of all of the documents that contain that keyword, and we sort that list ahead of time by how many times that keyword appears in that document. And so then when somebody searches for that keyword, you just go get your list and you take the head of it, and that gives you your documents that match. And so it's very quick. It's much more quick than actually having to scan every single document and see if the keyword actually exists in it. That would be terribly slow. Similarly, with vectors, there are indexing operations that we do. pgvector supports the IVF flat indexing type. And this index type, what it does is, let's say you've got 1 million vectors that you want to build an index over. In this case, we've said we want 2,000 lists in this index. And so it's going to create 2,000 lists of vectors. It's going to automatically cluster all of your 1 million vectors into 2,000 different clusters that are most compact, so that every vector in each list is most similar to all of the other vectors in that list and less similar to vectors in other lists. And then it's going to compute the centroid of all of those lists. This is just vector math. And so each list can then be looked at as the centroid, and everything will be closest to that centroid in each list. So now when I do a query, and I want to look up and find the nearest vectors to my query vector, I only have to brute force the 2,000 centroids. I can find the list from those 2,000 that has the most likely candidates that are closest to my input. And then I can brute force all of the ones in that list. I don't want to do the math of 1 million divided by 2,000. I think it's 500, but that would be another 500 vector comparisons. So in total, we would do 2,000 to find the list. We would do 500 across that list. That's 2,500 comparisons or vector distance calculations rather than the full million. So 2,500 is much faster than a million. The trade-off here is around edge cases. Like if your vector is on the boundary between two lists and it only slightly falls closer to one list than the other, then you might actually miss some other vectors from that other list that are also near the boundary. And that's why this is an approximate nearest neighbor search. What we can do in those cases, to handle those cases, if we find that our recall is bad, that we're frequently missing vectors near the edge in our results, is we can turn up the number of probes. And the number of probes is basically how many lists do we want to actually look at or consider. We can go from one probe of just considering the 500 vectors in the very nearest list to 10 probes. And then we'll actually consider 5,000 additional vectors across 10 different lists. And that will make sure that if anything is on any of the edges, we'll get that. But again, this is 10 times more expensive given the fixed cost of 2,000 up front. You can do the math, but the run times are actually very predictable. If you're doing this on a CPU core, it's always the same number of floating point operations. And so you can measure. You can say, how much latency budget do I have? How important is it to actually get every single record back or not? If you, good, yeah.
This vector cosine ops, was that table you defined previously as?
Great question, yeah. You actually need to build these with the matching operator that you will use. And so in this case, we are doing a cosine operator against our index. So we'll generate the index to match against the cosine operator. If you want to use the Euclidean distance or the dot product, you would substitute that here as well. You can build as many of these indexes as you want. So you could have 3 indexes, 1 for each operator, if you wanted to cover it that way. There's a lot you can do with these indexes. You can build partial indexes in Postgres that only cover certain portions of the table. So let's say you have some other criteria in the table where, like, maybe it's some document is part of a collection, and you only want to search for documents in collection 32. You can build a partial index that only includes documents from collection 32. And actually, what we found at Instacart was we didn't need vector indexes because all of our queries were scoped to very tight constraints where given the user ID, given the store that they were shopping at, given all of this extra criteria, we could winnow down the number of possible vectors to some subset far smaller than 10,000, and then we could just brute force the answer. And it would be an exact answer. And it would be very fast.
So what are the pairs? I think that's confusing. Like, are the pairs from the documents, or is one part of the vector pair the search pair, the search query, and the other part of the pair, the document repository?
So the question was, what are the pairs that we're calculating distance from? And it's whatever you want it to be. In the clustering case, the pair is going to be 2 documents. In the query case, you'll be comparing the incoming vector, the query vector, to a document vector, and to actually all of the document vectors. Clustering is a very expensive operation because you actually have to compare every vector to every other vector to find out what vectors are closest to each other. So this is like an n-squared operation on your vector size. Creating these indexes is a time-consuming process. And so you might want to consider. If you've already created your index, one of the very cool things about Postgres and pgvector is that anytime you insert a new record into the table, it goes into the index. The index is persisted to disk. If your database catches on fire or whatever, you can be assured that that data is safe and sound as long as you've gotten the response back from Postgres that in fact your transaction has completed.
But for the other case, first case where you have a search query and you're trying to match it to something in the repository, you wouldn't use an index, right? Because index has to happen before search time.
That's correct. You have to create the index before you can use the index. If you don't have an index on the table and you run that query, let's see, like this, Postgres will accept this query with or without an index. Postgres has a very advanced query planner. It will look at all of the indexes on the table given a particular query, and it will use statistics about the data, the number of rows, the different predicates in your query. In this case, the query has no predicate. And if the table has no index, this will be a full table scan. It will actually do this comparison against every vector. Now, if you have an index, on the other hand, it will use the index to take this shortcut that I've described. And so that's the magic that PGVector gives you.
In this case, like this is for the clustering case, right, where you're doing all n-squared pairs in a join table called vector pairs. That's what this example.
This is a very generic example, so I probably could have picked something more explicit. You could say that the left-hand side is query vector, and the right-hand side is documents.embedding. And in that case, that's what you would write, and then you would be selecting from documents. And that's how you would query that table. But again, you would have to generate that user query at runtime because what they're going to give you is a piece of text. So then you would call PGML embed on that piece of text. And I think we'll get into more examples like that in a little bit further down. So I'm going to go, I think we've covered indexing and some of the trade-offs there. There's more work being done on PGVector right now to improve. There's a lot of research going on around vector indexes. There's a lot of trade-offs. There's at least a dozen different vector indexing algorithms, but they are all some kind of trade-off between build cost, runtime cost, accuracy. IVF flat is a pretty good first stab that makes pretty balanced trade-offs amongst all of those things. So I think, Sid, to your question, this is a better example of what you might do. And in Postgres, if you want to start building these queries in Postgres, let's pretend that we've taken, there's a blog post I'll mention on the website that walks through all of this in depth of what you might want to do. But you have let's say we have a set of the Amazon movie reviews from all customer reviews for all of the Amazon DVDs for sale. So there are millions of these customer reviews. We can create embeddings out of all those customer reviews. We can store them in a table. And that'll be our documents table for this example, where we have millions of user reviews. Now, when somebody comes in with a query and they want to find a movie similar to that query, we can use PGML to generate the embedding for that. In this case, we're looking for the best 1980s sci-fi movie. And some people may describe in their review, they may use the keyword best 1980s sci-fi movie, but they might also say best 1970s sci-fi movie or worst 1980s sci-fi movie. And it's these like very subtle modifiers and nuances that embeddings are really magical about capturing the entire sentiment and not just over-indexing on particular keywords. So the quality you can get with a recall like this is pretty cool. This, when you have a with request as, this creates a virtual table in Postgres. This is called a common table expression. You can begin any query with this, and the content is any other query. Whatever comes out of that query, in this case, it'll be an embedding. So for the rest of this query, and we can chain multiple ones of these, that's what the select ... is going to do in the next slide. But we'll have a virtual table in memory. It'll have one row in it. That row will be a single vector named embedding, and it'll be generated on the fly from the best 1980s sci-fi movie using our model. So then we can actually do the cosine operator because we've actually built an index on this table in the previous slide. This will be very fast. This will be very efficient. And we get the full power of SQL. This doesn't have a limit. You probably should put a limit. Otherwise, you're going to be pulling back 5 million documents, and Postgres will know that. It'll know that there's 5 million documents and you didn't put a limit, so it'll just ignore your index because it's not going to do any good anyway, because you're going to need to calculate the 5 million dot products anyway. Because that's what you're actually selecting. You're selecting the cosine distance. So the Postgres Query Planner is smart. It will try to help you out, but you also need to be a little bit diligent when you're thinking about, what do I really want? What do I really need? The PostgresML isn't only limited to embeddings. There's lots of things that you can do with these large language models. Hugging Face has this concept of tasks that we've also adopted. Some of these tasks can be text generation, it can be text classification, it can be translation from one language to another. There's several dozen of these, but this is an example of using PGML transform, which is a second function that will also download a model from Hugging Face. In this case, we haven't even specified the model. Hugging Face has some default model. This is a bit of a foot gun because they may change that default model and your application may be using a new model that you haven't tested. So be wary, but you can also specify the model to this function. Although I was trying to keep these slides slightly simple. They do take keyword arguments, and you can anything you can specify to any of these API models, there's a way to pass the keyword arguments down all the way through. The output of this example here will be whatever the output of the Hugging Face model would be. So in this case, Hugging Face returns some JSON. It's going to have like a sentiment colon floating point number. Postgres has all of the JSON operators you need, so then you can dig into that JSON object coming back. And this is where I think the true power of SQL as a platform becomes really interesting, because if you think about all of the thousands of chatbots being built with LangChain today, it's sort of like the iPhone moment when everybody was building a flashlight app back in 2008. The very standard model is I have my user prompt that I want to chat with. You take that, you pass it to OpenAI. That's a remote data center call. It takes several hundred milliseconds. They have to actually then run their model on it. They give you back no longer one of the best quality embeddings, but they'll charge you for it anyway. Then you take that embedding, you pass it to your vector database, you look up a bunch of context that you want to use for prompt engineering with your chatbot. Maybe those are help documents that your support center has, or whatever. Maybe that's a movie catalog because this is a movie guru chatbot. You get that context that you've written all these documents about movies or about help for your support center. You pull back the English language text out of your database, and you pull back as much English language text as OpenAI's models will take in their context windows. You put your prompt on that. You say, given this information, you are a helpful chatbot. Please respond to this prompt. And you paste all that together. You send off 30 kilobytes worth of data to OpenAI again. They run it through their text generation model. They send you a response back. Then you go ahead and send that response back to the user. With PostgresML, you can do all of that in a single query inside the database. So there's no network transit. There's no memory copies. You create your embedding in the first CTE. You retrieve all of the relevant documents in the second CTE. And then in the third query, you pass those as concatenated inputs with your prompt to another large language model. And you can actually start stacking and chaining models with these CTEs as much as you want. One of the things that we found very useful is that cosine similarity is okay. It's good and fast, relative to, say, an XGBoost model that re-ranks. But an XGBoost model that re-ranks is going to be much more accurate if rankings really matter. So you might actually want a step number 3 to be re-rank with XGBoost, and then step number 4 to be, go ahead.
The text generation can be an online endpoint access, right? Because you don't want to load a model in your database. You just want to call OpenAI's. Can the task generation be online, remote executions?
I didn't.
The task, can it be a remote execution?
Can the task be a normal execution?
Yeah, the transform, it's going to happen in the database, right?
The transform is going to happen in the database. So all of that text document for the prompt engineering and context will stay inside of the database. And so there will be a much lower network data transit cost. It's going to be pointers in memory or a mem copy if necessary. And so you're talking about many kilobytes, potentially megabytes worth of data that doesn't need to get sent over the wire. And so we get, compared to OpenAI and Pinecone implementations doing the same thing, it's usually a 10x speed up.
I think the question was, can the model be hosted somewhere else?
Oh,
Not on your database?
You could. If you wanted to do it with PostgresML, you could have a foreign data wrapper to a different database instance. And you can set up that, and you can query that different database instance. If you wanted to retrieve all of your documents from Postgres into your Python application and then send those off to OpenAI and do a hybrid approach, you can do that, absolutely. But you're then now paying the network transit cost. And I think we're almost done, but I want to close with this SDK slide. I've just shown, we covered machine learning in theory, we covered SQL and how to do all this in depth. We've gone a step further and we've created a Python SDK that implements all of these SQL queries for you. It gives you, again, the functions with inputs and outputs that you actually want and need to know. You connect your Python application to a Postgres database. You create a collection of documents. You give it some arbitrary name for your collection. You can then upsert documents into that collection. If you want to go ahead and generate the indexes, you can do that with a single function call. We'll enforce all of the best practices and the most efficient query patterns with this SDK. And finally, you can just do your vector search. And you can get those documents back that you might then want to pass on to OpenAI, as you mentioned, Sid. We're extending this, though, to create chainable API SDK function calls so that you can do a vector search. And then instead of materializing the results immediately, you can call .text generation. And you can actually do it all in a single execution to get the efficiency back at the application layer. It's worth mentioning that if you try to do a bunch of LLMs inside of the database, inside of a single database, you're probably going to knock that database over pretty quickly. PGCat, I think I mentioned early on, is our other project that acts as a router. It handles sharding, it handles replication, it handles failover and load balancing across many different Postgres replicas. And so you might want to look into that project as well.